Thank you, Martha, and thanks to the organizing committee for inviting me today. So I'm going to, as she said, going to talk to you about film crystal silicon photovoltaics. And what that means to us is that we're after good quality crystal silicon on an inexpensive substrate made by methods very similar to the way amorphous and nanocrystalline silicon are made, and therefore having a cost structure something much more akin to thin film silicon than to crystal silicon. And I'll be talking about different elements of this, but we're thinking about a crystalline seed where these diagonal lines are supposed to represent the crystallinity in some abstract way, with an epitaxial crystal silicon absorber on it, and then some kind of emitter. We're using heterojunctions at the moment, and the light trapping is shown also. So what I'd like to do is first tell you why we're working on film crystal silicon, and then I'll go into our results with epitaxy, talk about our test cells. We grow these first on wafers in order to understand what the epitaxial quality can be like at the temperatures that are compatible with these low-cost substrates. We'll get into a little bit of the physics of thin cells, and then finally talk about our first steps towards epitaxial solar cells on seed layers. So why would you... can you push that arrow out of the way? It's a little distracting. Thank you. So, plenty of sand. It's environmentally benign. There's a new paper every 30 minutes in silicon. It's a little bit daunting. I don't read them all, but what we can do is use the enormous silicon literature that's out there and just look up those things we need to do photovoltaics. So we use a huge base, also an industrial base. Market acceptance will be good, we think, if we can succeed. There's a very low cost potential at high efficiencies. Right now, the wafer accounts for a little over 30% of module costs, but you definitely have to keep the efficiency high to reduce the balance of system costs. So again, we think you can get over 15%. I'll show you that these thin cells tolerate defects and impurities much better than a wafer cell. You use a lot less silicon, low energy inputs, and you get the advantages of monolithic integration that all the thin film technologies have. There are a lot of challenges ahead, though. This is a very difficult project, really. The low-cost substrates we've identified so far are basically display glass, which has the advantage of being thermal expansion masked to silicon, and some special metal foils I'll talk about. And that means that you have to keep the epitaxy temperature down. The thermal budget will probably only allow you to work at 650 to 800 degrees Celsius. You have to keep the epitaxy inexpensive, scalable, and high rate. You have to, this is the hardest job probably, the one we've worked the least on actually, is the high quality seed for the epitaxy. And of course you need excellent light trapping because of the indirect gap with silicon. So why is the wafer over 30% of the cost of a module today? And with 18 months energy payback time? Well, the feedstock itself is 30 cents a watt. And when you're aiming for, say, 50 cents a watt, as the current DOE goals are, that's a lot to pay just for your raw material. Now, so this is the present wafer technology. You add carbon and heat. So you coke the sand and you get metallurgical grade silicon. It's got a lot of impurities in it. This should say HCl here. As you make trichlorosilane or silane. Then you have another heated step to plate out the silicon feedstock, or another high temperature step to do it in a fluidized bed reactor. Then you add more heat energy. You have to go over the melting temperature of silicon. Then you throw away half of it as sawdust, and then you use 10 times as much as you need. So it's a wonderful technology. It accounts for 85% of the PV that's sold today and will continue to dominate for quite a while yet. But it's a kind of a dinosaur from the computer industry, really. These wafers were invented for another purpose, and they've been borrowed into photovoltaics. So what we're proposing to do is go back to the purest product in the process and directly deposit enough silicon for light absorption. And we think, as I'll show you next, that Hot-Wire CVD is the best low-temperature scalable epitaxy available. But first I want to talk about light, because the question I always get is, can you really make silicon thin with its indirect gap? Well, So this shows the one-pass absorption of the solar spectrum for a 1 micron up to 180 micron cell. So you already need a little light trapping at today's 200 micron cells in order to capture more of the light out to 1200 or so. What you see here is how much total current you get in one pass through, well, here's the wafer silicon, or what we project might be wafer silicon someday. You can see you get about 40 milliamps per square centimeter, and that's what the good cells get. This regime here that's darkened, the film crystal silicon regime, has been blown up over here. And what you can see is that if you could be even 15 microns thick, you would have over 30 milliamps per square centimeter. And that's pretty easy, even at 3 microns, 5x light trapping, which means that it behaves as though it's 5 times thicker. Or in other words, you have to be about 60% of the Oblanovich limit, which could be 50x light trapping. It's not that extreme. So we think you can easily get over 30 milliamps per square centimeter. All right, so let's look at the experience of people who've tried to get close to that. And this here, I brought together the literature data for, well, these blue triangles, for example, are thinned wafers. They just took wafers of silicon and thinned them and tried to find out what happened to their currents. And you can see it didn't hurt them at all, really. Some of these other people are doing epitaxy or epitaxy and wire transfer. There's a variety of things. I don't want to get into too much detail on it. And they're all well over 30 milliamps. This is that 30 line. And this is what we're aiming for, is to be in here. This is nanocrystal silicon at about 1 micron thick. This is almost 2 microns thick. So the critical ones to look at, though, is this 20 micron cells, epi on annealed porous silicon, well over 30 milliamps from IMEC. This one's almost 30 milliamps per square centimeter at 1.85 microns in what you'll see on the next slide is not such great material. So we think you can get to the current targets. Here's the efficiencies of those demonstrations. There are a bunch of them over 15%. Again, we're trying to push the boundaries down to here. Now you see the nanocrystalline, and well, the problem with this cell, this diamond cell, which had the 30 milliamps per square centimeter, is that it was crystallized amorphous silicon on display glass from a CSG solar. And they did an incredible job of getting as much as they could out of that material. But let's face it, it wasn't such great material. It was micron grains, and they never got above 500 millivolts. Okay, so there's a lot of room to improve the silicon material quality and therefore improve the open circuit voltage. So I want to now turn over to our epitaxy, and I'll come back to the devices in a minute. So what is Hot-Wire CVD? Well, you heat tungsten filaments up. Well, we use 1 or 2 normally, but industrial companies are using many, of course. It's widely used in the diamond industry, also for VLSI nitrides now. You flow silane over it. That's the silicon with 4 hydrogens, schematically shown here. We're at a fairly moderate base pressure of about 10 to the minus 7 torr, so everything we do tries to be industrial. It's very similar to what amorphous silicon does. And then these silane radicals come down. The sample's on a heated substrate, as I said, about 600 to 800 degrees. So it's a lot hotter than amorphous silicon in order that you can do epitaxy. It has rather unique growth precursors. Depending on your conditions, you're either in silicon or Si2H2. We can do high-rate epitaxy anywhere above 620. People often ask me, why not just do it with PECVD? Well, you basically can't. You can do some of these things. You can get good quality if you grow really, really slow. You can get a good utilization as long as you don't worry about high quality. If you just do thermal CVD, you have to go all the way up to 1,000 degrees to reach the same rate. So the substrates we're working with would melt, or you'd get a lot of diffusion of metals into the sample. So we're forced down to that temperature regime. And if you're interested in how this works, one good reference is this one by Martin et al. Last year for a comprehensive growth model we've used to try to tune up the project. So these are some fairly early samples from our work showing the epi on wafer, selected area diffraction, the substrate and the film look the same. When you do high-res TEM, X-ray pole figures, we know this stuff is epitaxial. When we raise the temperature up into the 600s, we no longer have a limiting thickness for the epitaxy, so we can get a 40 micron layer if we want, although we don't anticipate going that thick. Most of the defects, as you can see here, enucleate at the interface, dislocations, twins. And it turns out that by controlling the purity or blowing off the oxygen before we start, we've been down actually into the mid 10 to the fourths in defect density. And we think you can really do better if you control all that. So we think it's pretty promising. Here's a picture of 10 to the fifth per square centimeter. As I said, we've come down a factor of 2 lower than this, actually. This is an SEM image. You can see the dislocations coming up to the surface with about 20 microns between them. And each one of those spots where the dislocation hits the surface kills the cathodoluminescence. This is, you use an electron microscope, you put electrons in, and you look where luminescence comes out, and you can see those dark spots. So it's important to reduce the number of dislocations. But when you have a 5 micron thick absorber layer or a 3 micron thick absorber layer, 30 micron spacing between defects is just fine. Again, that's a big advantage over wafer silicon because the photogenerated carriers just have to get to the surfaces before they find their way to a defect. So it's much more tolerant of defects than it would be in a wafer. We've recently gone out to almost 2 microns a minute. We haven't found a fundamental limit yet. So far, it's just how fast we can throw the radicals down by putting in more wires and coiling the wires tightly and flowing more silane. So we haven't had a point where we find we're just growing too fast for the film to assemble into a good crystal. That's what I mean by no fundamental limit. The epitaxy time then for, say, a 4 micron device would be about 2 minutes. Right now, there's 15 to 60 minutes for the nanocrystalline and amorphous silicon. And that's one reason their capital costs are a little too high, right? Is because you have to put a lot of equipment to grow stuff that slowly. And that's, by the way, the big advantage. One of the big advantages of cadmium telluride is that they grow really fast. This is almost as well as we have to do. There's really diminishing returns for raising the deposition rate any higher. This is a model that the analysis group at NREL did for us of the costs of the epitaxial deposition step alone. And you can see, so you're getting down to, say, 10 cents a watt for a 15% cell. As you go out to even 4 microns a minute, you know, we've still got a little to gain by going from 2 microns to 4 microns a minute. But you can see where the typical nanocrystal silicon rate is here at about 60 nanometers a minute. So this is a different animal because it's higher temperature. That's the price we pay. By the way, when they did the full cost modeling, they came to about 65 cents a watt. You should take that with at least a 20% grain of salt, I think. It's very hard to predict what new technologies will really cost when you finally shake them out. But it makes us think there's a lot of promise for the technology. So we started, as I said, with epitaxial cells on dead wafers. And we're going to pay attention a lot, as I talk about devices, to open circuit voltage. Why? Because, frankly, we haven't really optimized the light trapping yet. First, you've got to make sure you have the material quality, the seed and the epitaxy. And second, because open circuit voltage is the right thing to track to know how good your materials are. So what's open circuit voltage in these materials? Well, it's basically the water level in a bucket where you're dumping water in. The water you're dumping in is the photogenerated carriers. By the way, this analogy works pretty well mathematically even. Recombination losses are these holes, and you have to keep patching them. First the biggest holes, and then the smaller and smaller. And we've been patching holes for a couple of years now and getting the voltage up. What's good is that it measures the silicon PV quality right in the device, so you know everything counts. The bulk, the surfaces, and surfaces are very important in these thin devices. And when you get that voltage, you don't only have voltage. It really sets the useful thickness of silicon that you can use, and therefore it will set the short circuit current for a certain ability to do light trapping. What we make is these dead wafer cells where we use a very heavily doped crystal silicon wafer. It has a lot of Auger recombination, so photons that are absorbed down in the wafer do not contribute current, except maybe the first half micron or so. We actually think you get maybe a milliamp per square centimeter from from the top micron of the crystal silicon wafer according to our modeling. So then we have an epi layer, the amorphous silicon heterojunction, ITO contact, and here without any hydrogenation at all, so without doing any passivation in this layer, we get up to about 570 millivolts. The point, though, here is that these are EBIC, where you put the electrons in and you look at the current that's collected. And every one of those dark spots, again, is some kind of dislocation or defect that hurts the efficiency of the cell. So on the left in blue, the IV curve corresponds to a fairly high density of defects, above 10 to the 6th. And as we reduce the defect density down to 10 to the 5th, the voltage goes up and up, because that dislocation is eating up the carriers that you prefer to collect at the top surfaces. At 10 to the 6th, there's about 10 microns between defects, but that's still not quite far enough apart. So this cell is about 6.7% already, no light trapping, rapid thermal anneal, or hydrogenation, all the tricks that other groups that have worked in polycrystal silicon always apply to improve their material quality. Okay, so what's going on? Well, just a little digression onto physics, and you can see more of this in Kirsten Alberry's paper. Basically, when you put photons into the semiconductor, imagine an ensemble of photons coming in and hitting at the same spot. They would produce a cloud of carriers that diverge from that spot. And how far does that cloud extend? Well, one diffusion length, because that's the distance at which they recombine. So now if you overlay a thin cell over that that's thinner than the diffusion length, you'll collect most of the carriers. In fact, if you do it analytically, you find out that the cell thickness has to be less than about the diffusion length over 3 so that you get those carriers before they recombine. Well, now you imagine unpassivated dislocations, as in the last experiment. The closest dislocations are going to limit the diffusion length, because on average that's where a carrier is going to find a defect to recombine at. And so that sets another thing, and that gives you this 6 times the cell thickness. If you have a 3-micron cell, you want the dislocations 20 microns apart. The other thing, besides the dislocations, are impurities. Now, as I said, we don't have a very pure system. Our base pressure is 10 to the minus 7 torr. But fortunately, film silicon PV is a lot less sensitive than wafer. Why? Because that required diffusion length of 3 times the cell thickness. Well, there's a random, if you imagine a random walk through a field of n, a density n of defects, the distance you go will scale like that impurity density to the minus 1/2 power. What that means is a 3-micron film is immune to about 10 to the 4th times more defects than more point defects or impurities than a 300-micron wafer. So we're 10 to the 16th per cubic centimeter of nickel or tungsten or titanium. That's this red line. This is the famous work by Westinghouse from a long time ago. They're looking at the solar cell efficiency falling as you put impurities in, and when they get up to 10 to the 13th, 10 to the 14th metallic impurities, they're in trouble with nickel or titanium. Well, if you make it 3 microns thick, there's no problem even at 10 to the 16th or 10 to the 17th. So even though we have tungsten in our samples at, say, 10 to the 14th or maybe 10 to the 15th, we don't think that's a limiting factor at all. Okay, so I said we hadn't hydrogenated yet. Well, we have. Here's what happens when you hydrogenate a wafer cell that's not too good. This is one with a lot of dislocations. And when you start putting hydrogen in, suddenly the voltage jumps way up. And this is still, by the way, no light trapping, a single pass of light through a 2-micron layer. And it's not bad. In fact, we have now a confirmed 625 millivolt cell, which shows that the power of hydrogenation to take care of defects. And I'd say we've really just started this, and we have a lot more work to do optimizing it, because this is a very special film. It doesn't have grain boundaries, right? So the hydrogen can penetrate well, but then it has to find its way to the dislocations, and you have to keep it there. So what's really required for a good 3-micron film? You need a minority carrier diffusion length of at least 10 microns, and that means the lifetime has to be about 100 nanoseconds. Now, that's really low. Crystal silicon, people are sitting there saying, they can't do much without being in the microseconds, tens of microseconds at least in multi. To do a really good cell like a sun power cell, you have to do milliseconds, tens of milliseconds. But you do need excellent surface passivation, and that's why we work with the amorphous silicon heterojunction emitters, where we can make 19 and 20% cells on wafers. And we use an N plus epi to put in a back surface field in our N-type solar cells, and of course you need the excellent light trapping. So now I want to spend the last part of my talk telling you about our cells on seed layers. Here's the first one. So you want to know whether you can do it on display glass. So you get the kind of what you imagine, at least, will be the ideal seed. And we've done just a little work here with Corning Incorporated, who does layer transfer for the display industry, as I understand it. They've transferred P+ in this case. We grew epi by Hot-Wire, put on a heterojunction cell. And it's we consider this practice for laser crystallized silicon seeds on display glass. And here, so far, we're at 533 millivolts. We actually haven't spent that much time on these because it's not an inexpensive industrial seed. Layer transfer, we think, is probably too expensive even to be used as a seed layer. So another type of seed we're working on are these metal foil substrates. And this is rolling assisted biaxially textured substrates. So what are these? These are kind of a substrate that was industrial scaled for superconducting wires. There is a company, actually I think two of them, that are making these foils. It's been known for a long time that if you roll foils, that it breaks the symmetry and you wind up with all oriented grains. And in fact, as you can see here, you can come up with 50 micron grains. This is a nickel tungsten foil. And then you put heteroepitaxial buffer layers on them to keep the silane from reacting with the metal. You want to prevent silicide formation and metal diffusion. Right? And these are all very near 100. All the grains are within a few degrees of 100 orientation, and they're oriented in plane as well. And so in this particular implementation, by the way, we're working with a ORNL and also a startup company called Ampulse that's working to commercialize this kind of thing. And ORNL puts mag oxide and gamma aluminum oxide on the nickel tungsten for this, gives chemical compatibility with our growth. And then here's the pole figure, the 111 pole figure for the nickel. And here it is for the silicon. It's rotated by 45 degrees. Well, it turns out it rotated 45 degrees at this interface, 45 at that, 45 at that. So the net is 45 degrees. But what you can see is the crystalline quality is just as good, or in fact sometimes better, than the underlying 100 foil. Okay, so this kind of sample has gamma aluminum oxide at the top, and we have no trouble doing heteroepitaxy on gamma aluminum oxide. So one thing we have done is to work on ideal single crystal gamma aluminum oxide substrates to see if you can actually get devices with these heteroepitaxial layers. This one's on R-plane sapphire. This is, again, Hot-Wire epitaxy, an N+ back layer and N- layer. And we get over 400 millivolts that way. Here's the quantum efficiency. It's behaving, even though it's 2 microns thick, it's behaving a lot like a 1 micron, 1-pass cell, which suggests that the diffusion length is still not long enough. It's maybe a micron thick. So it has a whole diffusion length of about a micron. We also do this on gamma aluminum oxide, which is the same phase that we're getting on the RABiTS substrates. By putting them on an STO wafer, we're able to test that too. Get about the same 400 millivolts. Again, hydrogenation. Here, hydrogenation takes care of an awful lot of the problems. And you can see that hydrogenation has kicked the voltage up to 582 millivolts. This is just a brief exposure to a plasma-generated hydrogen. It's an inductively coupled plasma at 610. After hydrogenation, we analyze the QE, and we find out it's now 2 to 3 microns. We do transient photoconductivity decay to get the lifetime, and we have about a 10 nanosecond lifetime. So we we're most of the way there. We'd like to get to 100 nanoseconds, so there's still quite a lot of work to do in improving the heteroepitaxy and improving the hydrogenation. Can you light trap? Well, good news is that these things are 100. We're growing 100, so we can just put pyramid texture in. We alter the recipe a little bit to make sure we only remove 1.5 microns of material, because this stuff is still a little expensive, and we don't want to just throw it away to etch in the pyramids to get light trapping. Now the light comes in, and it bends, and you get multiple passes. Also helps with the anti-reflection, because you get several bounces to get in. But the main thing we're after is getting some light trapping. You can see when we add the pyramid texture to these devices on Sapphire, the currents jump from 11 to over 20 milliamps per square centimeter. Okay, so we can grow on aluminum oxide, and so we were also working, in this case, in collaboration with the Clemens group at Stanford, who does IBAD. So we're back to display glass here. And it turns out that if while you're doing sputtering or some other physical vapor deposition of your material, if you throw in an ion beam of some inert material, you can ablate away all the crystal grains that are pointing in the wrong direction. So you can develop a very strong biaxial texture. Now the grains are a lot smaller than on those RABiTS, but you can get all low-angle grain boundaries between those grains. And so here we've made, again, a solar cell. So we start with a display glass, which is reasonably cheap for PV, about $0.10 a watt, probably. We do the IBAD calcium fluoride, or Stanford does it actually. Puts evaporated germanium on, and then we do hot-wire epitaxy and put our devices on that substrate. And we're just getting started. A very recent result that we've just submitted for publication is a 375 millivolt cell. The diffusion length is still below a micron. We're still asking the question, the grains are pretty small. Will low-angle grain boundaries really provide the 10 micron diffusion length that we need? Well, we'll see. I guess from all these talk about different seeds, I guess it should be obvious to any of you that we're still open to the new perfect seed that's going to come around next year. And if one of you has it, please come and talk to me after the talk, and we'll build a collaboration, because we think we're getting the tools to do the epitaxy and make the good devices out of whatever you have. So here's our progress over the last couple of years. This is the kind of slide you usually only make for sponsors, but I thought it was interesting enough to show you what we've been doing. So this is on the dead wafer stuff I showed you. Here we're aiming for 600 millivolts at least, because we think it's needed for 15% cells. This horizontal line here is the voltage that nanocrystal silicon gives today in the amorphous nanocrystalline tandems. Here's where CSG solar got. Here's where we are on dead wafer. Here's where we are on Sapphire. I showed you that 582 millivolt cell recently. And everything's happily still trending up pretty well. We don't think we've at all reached the limit of where this can get to. Now I add in the seeds as the hollow symbols. And what you're seeing is this is the layer transfer silicon. And here's where we are on nickel foil and on the calcium fluoride on glass. So we do have a lot of work to do, and we welcome collaborators. So to summarize, we're doing this Hot-Wire CVD at glass-compatible temperatures, or at temperatures where it doesn't break down the buffer layers and get too much metals into our films. We've made 30-micron dislocation spacings on wafers. We got heteroepitaxy, so it's possible if we have a good inert surface. Almost 2 microns a minute. We have demonstration PV cells. I showed you a lot of details on this. Light trapping isn't too difficult on 100, but really IMEC and others have shown that you can do RIE, or chemically etched light trappings, even if it's not 100. We really need 100 nanoseconds. So far we're at about 10 nanoseconds. But we think you can get to 15%, retaining an awful lot, actually improving on wafer silicon technology if we can get there, because the cost should be so much lower. A lot of hard work and good ideas are still needed. I've talked about the main things we still need. I want to take my last minute and give my sincerest thanks to the people in our group who've done really all the hard work. on this, especially Chaz Teplin, who's here, Dave Young, Falah Hassoun, Paul Stradens. We had some great postdocs that have done really important stuff. And then there's the NREL characterization support, our technicians. We've worked hard with Ampulse on the sapphire work and the foil work. The seedwares on foil and glass come from ORNL, Corning, and Stanford. And we have a lot of sources of financial support. So I thank you for your attention, and I'm glad to take questions.